Good afternoon, good morning, or good evening, depending on where you're calling from. I'd like to introduce my research work on chicken feather and specifically discuss the use of the inverse gas chromatography method to determine the surface properties of chicken feather mats. Why this study? Oil spill is the accidental discharge of crude oil or its refined products into water bodies. It is a global challenge, but my focus is a global challenge, but I'm focusing this research in Nigeria, an oil-producing country in West Africa, and specifically the Niger Delta region. The presence of oil in our water resources affect the quality and also the aquatic ecosystem. In 2011, we experienced the Bonga field oil spill with 1.1 million liters of crude oil, which is about 35,000 barrels, contaminating a coastal strip of nearly 200 kilometers at the Nigerian coast. This required massive cleanup operation. Over the past years, oil spill cleanup is handled in three major ways: chemical, biological, and physical. All the three different methods have their advantages and disadvantages. But presently, the use of sorbent, which falls under the physical method, is preferred because it has less environmental impact. Sorbents are insoluble materials or mixtures used to recover liquids through the mechanism of absorption or adsorption. According to the current analysis of reports and data, the global industrial market of sorbents was valued about $3.7 billion in 2018 and is expected to reach $5.42 billion by the year 2026. Sorbents are classified into three different areas. We have the synthetic organic sorbents, inorganic sorbents, and natural sorbents. Feathers fall into the natural organic sorbents. I'm looking to use sorbents because they have high oil absorption capacity, low water pickup ratio, and they can be reused. Over 5 million tons of chicken feathers usually are generated annually from different farms globally, all over the world. This particular product is supplied by Plumo UK, and it is produced by mixing chicken feathers with biodegradable bicarbonate fibers to form these non-moving mats. Just for emphasis, a fundamental objective that we're looking at for this research is to find a high-value reuse application for waste feathers in Nigeria. The research context today, I'll just be looking at reviewing a little bit about chicken, then I'll go through the test that has been done before, which is the oil absorption test, and then also the water solvency test. Then I also look at dynamic vapor absorption tests with water and oil, and then look at the IGC result, which has also made a huge impact in this entire study. Now, chicken feathers, like we'll see in a picture I'll just display quickly, are very unique. They have hollow structure and contain rashes, barbs, and babblies. They compose mainly of 1% protein, 1% lipids, and about 8% water content. They're hydrophobic and they have oleophilic properties, which result in high keratin content. The absorption quality of the chicken feathers is determined by their surface chemistry and the microstructure of these feathers. Here we can just see the structure of the chicken feather. It's you see it has the quill at the ending, then it has the rashes which runs through the entire middle section, and then we have barb and babblies. Every one of these parts of the chicken feathers, they play a great role in its ability to be able to take in water. And the hollow structure enables us have a whole lot of retention of liquids. The hooks and hooklets, they now have air pockets, which make it easier for the feathers to float on water. Like this picture we see here on the right-hand side is birds after an oil spill from the water. We see that their feathers are soaked in oil. Now, this is because there's a whole lot of attraction between the feathers, the birds, and then oil. This can be due to the intermolecular bonds that exist between the hydrogen carbons that are present in the feathers and the and the beds. The very first test that was done, we used the like the oil sorption capacity test. I'll just briefly talk about that. And that's I used the ASTM F72606 method, two different dynamic simulated system, and then both the static system at both room temperature and pressure. And then the oil sorption capacity was calculated using the equation here. So I'll just explain the static system. The only difference between the dynamic and static systems is that for the dynamic system, a shaker table was introduced to just get some form of vibration. So for the static system, about 700 milliliters of tap water is poured into 1 liter of glass beaker, and 30 ml of engine oil is poured to create like an oil surface. Then I cut about 0.9 to 1 gram of feather mats and then weigh it. After weighing, I put the feather mat into the oil and water mixture, and then after 15 minutes, the product is weighed and the oil retained is calculated. Now, this same experiment is done in triplicates, and I'm also doing it for other conventional products that we have here. The first one is the polypropylene pad, which throughout the entire study, we used as a comparison base. The next one is safe soak absorbents, and then we have the Drizzt absorbent granules, and then we have the woodlows. The picture on 5 is the chicken feather mats. So basically, this same test is done also for all these products, the conventional products. And then this was the results that was got. In this result, we see here that I used different chicken feather mats with a density of 20 kilograms, a density of 27, and then also 40. And then we see that the chicken feather mats had the highest, or 20 had the highest sorbency of about 26 gram per gram. And then the next product was the polypropylene, was the woodlows fiber, and then we have like the polypropylene oil pad. And then the least that had the least sorbency was hydrocarbon granules. Now, also, another test that was done was the water sorbency test, just to also see the amount of oil and the amount of water that these products are able to take in. Because, as earlier mentioned, we want to have a low water taking ratio. And so we also saw that we had the feather mats had a low taking ratio of about 0.4, the feather mat which was used in this entire study. And then we also have the polypropylene had a lower taking ratio of about 0.3. A major test that was also done is the DVS. The DVS experiments, we performed the typical water vapor sorption experiment at 25 degrees centigrade for both chicken feather and polypropylene pad. And I'll just introduce the DVS. The DVS is developed by surface measurement system and uses the gravimetric principle. It allows the calculation of how much water penetrates a material as a function of the relative humidity. In the first graph here, we see that the sample is suspended from an ultra-sensitive recording microbalance, and a carrier gas is flowed over the sample at a specified relative humidity, and the DVS measures the uptake and loss of moisture. In the second graph, we see that the sample is constantly weighted throughout the experiment, and the point noted at different intervals of the relative humidity. And then for the last graph, we see where the isotherms are plotted, generated by the concentration and mass data. Some unique features why we actually looked at using the DVS is because it's a fully automatic sorption equipment, and it can be done under a wide range of temperatures and pressures. Also, fast equilibrium is achieved, and it has a very sensitive ultra balance of about 0.1 microgram, which is was very good because of the type of material that is being used. For the result that was obtained for our chicken feather mat in motor oil, we see that here we have that the blue line we have on the left-hand side is the target relative humidity of each step. So we change the humidity step by step from 0 to 95% relative humidity at low relative humidity range and 10% at a higher relative humidity range. The plot on the left-hand side is just like we see that the mass plot showing the kinetic information and then also the water isotherms. That's what we have on the left-hand side. Now for the result, we see that there was an uptake of about 1.3% change in mass at 95% relative humidity. Also, when we look at the isotherm plot of desorption on the left-hand side, we see that the hysteresis gap is wide, and this confirms that it's bulk sorption dominated mechanism. Now for the polypropylene pad in motor oil, we see that the uptake is less, about 0.1% change in mass at 95% relative humidity. And also we see that there's a narrow hysteresis gap, and this confirms surface sorption, which was the dominating mechanism. The major test which I'd like to spend more time and also talk about, which is the IGC, very unique instrument that we had and that we used. The IGC was first developed in the 1950s, but we have the first commercial system, which was developed by Surface Measurement Systems in 2009. The basic thing measured is the surface energy heterogeneity. And then also the IGC can measure different surface and bulk properties of powders, fibers, particulates, and semi-solid materials. And that's why I also looked at using this equipment. I'll just talk about the IGC principle. And we see here in this slide, it shows the animation of the IGC principle and shows the difference between the analytical and then the inverse gas chromatography. In the case of the analytical gas chromatography, the solid property is known, and then we get the quality and quantity information of the injected compounds. While in the case of the inverse gas chromatography, the known vapor molecules is injected over a solid sample using a carrier gas, which is like a mobile phase. And by measuring a time a probe molecule takes to elute through the packed column of the sample material, we can get the thermodynamic properties of the solid phase. So it's very unique, and it's just like the inverse. Now, surface energy. Surface energy is the most commonly measured property by the inverse gas chromatography. It is analogous to surface tension of liquids, and it provides information on the intermolecular forces that are occurring at the surface of the material. It's also directly related to wetting, the thermodynamic work of adhesion and cohesion. The IGC requires the specific surface area to determine the surface energy. That's why we first look at determining our specific surface area using the Betz theory. Now for the total surface energy, it consists of independent and partially independent components, which represents different types of the intermolecular reaction. We have the dispersive component, which is like the non-polar, the physical long-range interactions. And then we also have the Lewis acid-base component, which is the polar side of it, the chemical short-range interactions. I'll just briefly explain like the relationship of surface energy to different properties. Like when we have like a surface and then we increase the surface energy, we see that the wettability increases. Now, if we have like molecules in a system and then we increase the surface energy, we see that the force of cohesion increases. And then if we have a surface and we introduce a form of like disorder, we see that as we increase the surface energy, that disorder also increases. And then if we have like a system where we have like a big molecule and a small molecule, or intersystem, different substances, a fiber or a non-fiber, and then we kind of like increase the surface energy, the cohesion between the smaller molecules will decrease, thereby increasing the adhesion between the larger molecules and the smaller molecules. So this is just kind of like relating the surface energy to different properties. Now, I'll just talk about the best specific surface area. This is a theory that explains the physical adsorption of gas molecules on a surface, and it serves as a basis for the measurement of the specific surface area. The BET equation displayed fits the isotherm type 2 or 4 over this specific range of equilibrium. And then from the table, we see here that the chicken feather mat has a specific surface area of 1.5 meters squared per gram, which was a bit smaller than the specific surface area of the polypropylene pad. The polypropylene pad is the conventional material that is widely used for now, and then we are just comparing the chicken feather mats to the polypropylene. Now, when we look at the surface energy, the total surface energy, which is divided into two components, we have the dispersive, just like I mentioned earlier, and then we have the specific. So the dispersive surface energy was performed using the net retention volume for a series of alkane elutants. In this case, we use hexane, heptane, and octane. And then the dead volume was determined by methane. We used the Doris and Gray method, which was applied during the analysis, and the dispersive component was determined from the scope of the correlation. The specific contribution is obtained also by the IGC by measuring the retention volume of polar probe molecules on the sample. In this case, we use dichloromethane, chloroform, acetronal, and then toluene. For these three graphs here, it shows the individual surface energy profiles for all the three samples. We included motor oil because we also just wanted to have its own representative, which we used as throughout also in the different tests. So we see here that the blue line is for the dispersive component on all the three graphs, is for the dispersive components, which was given by the non-polar probes. And then we have the red line is for the specific component given by the polar probes. The green line is for the total surface energy, which is the sum of both the dispersive and then the specific component. All the three samples from what we got are heterogeneous in nature, and that means that like they have both high energy and then low energy sides on the surface. We see here, like if we look at the chicken feather mat, we see that the dispersive component contributes the major parts of the surface energy, and it's the same for all of them. So we have like the dispersive surface energy. We have here that the motor oil is the most active. And then for our specific surface energy, we see that the polypropylene has more functional groups on it than the chicken feather mat. And so it has the highest. That's what we have here from our result. So it has more functional groups and we have it higher specific surface energy. For the total surface energy, we have, of course, the highest still be motor oil, followed by polypropylene pad. So the chicken feather mats, like we see from here, is the most stable compared to all the others. For the total surface energy distribution, we did like a point-by-point integration of the surface energy profiles. And we actually just did this so that to be able to represent the heterogeneity of the samples in a more illustrative manner, because like we see here, it's the picture, the graphic picture, it makes it very easy to see and then easy to understand. And then we see that the wider the gap on the x-axis, the more heterogeneous the sample. So from the graph, we see that the polypropylene is relatively more heterogeneous and possesses some surface sites with the most different levels of energy. And for both samples, after mixing with the oil, we see that the surface becomes more uniform, and then also they have like similar energy sites. So that was the effect of also mixing with the oil. So for the specific free energy, which is calculated from the retention volume of the polar probes, it shows that the interaction of the polar molecules with the solid samples. And then when we have like a higher delta G, it means stronger reaction. And also, it means a stronger reaction. And we see that the chicken feather mat has the most interaction with this for all of them. The acid-base property, it provides like an empirical basis for the calculation of the surface energy with respect to acidity and basicity. And then we have like SC, which is called the surface specific character. Usually when our SC is less than 1, it means that the surface is considered to be basic. It has like more electron donating ability prevailing over the electron accepting. And then when the SC is greater than 1, it shows like more acidic character. When the SC is equals to 1, it just means that the surface is amphoteric. And from our graph here, we see that the surfaces of the sample are more basic in nature. They possess higher concentrations of electron donating surface functional groups. The thermodynamic work of cohesion and adhesion is basically like the work needed to separate an interface from like a bulk phase, which we also saw in that other display that was given to relate like the surface energy with cohesion and adhesion. So we see that cohesion is between the same sample, and then adhesion is between two different components. The higher the work of cohesion value shows higher tendency of aggregation in a sample. The chicken feather mat here shows lower cohesion than the other samples. For the work of adhesion, we calculate it in relationship to the motor oil, that we are relating both chicken feather mat and polypropylene pad. How well does it adhere to the motor oil? And we see here that the polypropylene pad had more higher affinity to the oil from our work of adhesion. Looking at the polarity and the wettability, the polarity profiles, we calculate them from the specific surface energy over the total surface energy. And we also see that the sample with the higher polarity shows better affinity with water. The chicken feather mat basically had a more affinity to water than the polypropylene pad. But the difference it did not adhere. It was not like so much water, but it just was, the polypropylene pad had less ability to adhere to water. So basically from all the different results and tests we had, we see that the IGC experiments, there was no limitation because of the kind of sample we use. We were able to get our results without any problem. We didn't have any problem at all. And then also, I could conclude that the chicken feather mat, because that is my main product, is a good sorbent. The adhesion to motor oil, it has low water uptake ratio, and then it has a good surface area result. Now, if we look at the entire comparison, we see that yes, the polypropylene pad kind of like got better results compared to the chicken feather mat, but it was not, it was just a situation where we also had the chicken feather mat having those qualities of being a good and a potential sorbent. And then we see that specifically also had the understanding that the chicken feather mat, its means of absorption was more in the bulk, was more in between the molecules, it was a bulk reaction, while the polypropylene was more of the surface reaction. So the detailed knowledge of the whole surface energetics, which was provided by the IGC, will help the products, to help to improve the products, to help to also know exactly what to expect in our field trial and also in the proposed end of life option. I hope with this kind of short but also long presentation, I've been able to explain my project a bit to everyone who has been listening. And then if you have questions, I'm happy to answer them. Thank you.
Thank you, Kaine. That was a fantastic presentation, and I'm sure all of the everyone listening will join me in thanking you as well. As Kaine said, we invite you now to submit your questions in the question tab. You can be able to find that in your GoToWebinar panel to your right. We have one question for you right off the bat, Kaine. It says, from the results obtained, we see that the polypropylene pads have a higher surface area than the chicken feather mat. What can be done to increase the surface area, which can invariably lead to a further increase in the amount of oil it can absorb?
Well, thank you very much, John. Basically, what we can do is, with the results we've obtained now, would go back and there are different things we can do. We could actually, instead of using it like in a fiber or in a mat form, we could actually use it like we could just get our chicken, clean them up, chop them, and then have it in a different format. So basically, we can have our chicken feather in a different format than the mats, and definitely this would increase the surface area. So it's either like if we decide to have it in like powdery form, or we decide to have it in just a whole feathers cut up and then chopped up and all that, we kind of like somehow we will just increase the surface area by changing the form. Yeah, by changing the form, basically, would consider different forms in which to have the chicken feather, and that can increase the surface area, which will also increase the sorbency ratio. Thank you.
Thank you. Another question here from Musab Osman. He says, interesting work. He was wondering, how did you measure the surface coverage, and what does N/NM refer to?
Let me see. I'm just trying to get to my slide to just see, but I think my colleague Mishan can help answer that.
Is that me? Okay, yeah, the surface coverage is basically different concentration of the vapor is injected, and according to the surface area of the material, and also we know the cross-sectional area of the probe molecule, we can then calculate the number of moles and how much of the surface is covered by that amount of the probe molecule. And then we want to cover basically to achieve a monolayer, and that is what the ratio of the number of moles covered to achieve a monolayer is then determined.
Okay, great, thank you. A question here from Ron Gray. How did you measure the motor oil surface energy heterogeneity?
Again, I might as well answer permission. Would you like to?
For motor oil, we did the same, like we put it in a column. So in this case, it's an oil sample, and then we put some siliconized glass wool in the column, and then put just several drops of the oil in the column and keep it with the glass wool. So the glass wool doesn't have any kind of interaction with the probe molecule. So the result will just from the bottle of interest, we put it in the column. That's how we did the experiment. And in case of some other fiber sample, we just simply put it directly inside our selenized column as well. I hope this answers your question.
Thank you. We have a question here from Ji Chen, and they ask, how many humidity points are needed to enable BET calculation?
Like in case of the BET calculation from the theory, you need to use the points from 0.05 to 0.35 for the calculation. And in this range, with the IGC method, we can put as much as we can, like normally at least maybe 5 points for the calculation of a good linear BET line. And in case of DVS method, we can also put different intervals in this range, like 5% intervals or 2% intervals if you just want to put more points inside the range. But you will see a very good R square if it's a good correlation between the BET theory to do the BET calculation. But at least 5 points.
Okay, thank you. We'll just wait a few more moments to see if anyone else wants to submit a question for us. Oh, great, another one from Ji Chen. Do you need to full cycle, or can you do a half cycle for BET calculations?
Well, I think you are regarding to maybe DVS technique, because with DVS technique, we can also perform some organic vapor sorption. And then in this case, you can do both sorption of desorption and adsorption. And then you can calculate the BET surface area from both sorption and desorption branches. And if the sample didn't change the structure during this process, you will get two very similar values from different calculation. But we normally just do with the adsorption for the calculation. And in case of IGC method, you will only get one result because it's just the illusion of the probe molecules. It's not for sorption and the desorption.
I guess not. Well, then in that case, we will wrap up for the day there. I'd like to thank you all again for joining us for the last webinar of the Surface Measurement Systems calendar for 2020. I'd like to remind you all that if you do have a taste for educational content, we have just launched the ticket sales for our IGC Symposium Online 2021. This is the first virtual edition of our North American IGC Symposium, and it'll be taking place on the 17th and 18th of February, and it will offer a full 2-day conference across a range of applications and industries with both professional and academic speakers, and we'll have a great raft of networking opportunities where you can just get in touch directly with your other attendees or engage in group discussions and live Q&As, and just a really great opportunity to kind of reconnect with the global IGC community after a year of slight separation. So if you are interested in finding out more about that, you can go to surfacemeasurementsystems.com/IGC-Symposium-2021. I'd like to take the opportunity to thank Kaine Chinwah again for giving another fantastic presentation and for taking the time to be with us today. Anyone who has any questions for Kaine or for our team, please don't hesitate to send them through to us at science@surfacemeasurementsystems.com. And likewise, if you have any queries about the IGC or DVS methods, or have any wish to have any samples potentially tested using and characterized using these methods, please email us at science@surfacemeasurementsystems.com. Thank you all again for attending, and we wish you a happy Christmas, season's greetings, and a happy New Year wherever you are. Thank you.